Section 4-3 is on the derivative of a quotient of two functions. The objective of this section is given a function that is a quotient of two other functions. Find an equation for the derivative function. So again, we're just adding to the set of rules that we already know for finding a derivative. And now we're going to look at the derivative of a quotient. So here is our quotient rule. And as its name indicates, it's called quotient rule because we use it to find the derivative of a quotient of two functions. So there's a couple ways that we can write this. We'll take a look at this first way to write the derivative of a quotient using a function notation is what we're seeing here. It says if f of x is equal to g of x over h of x. So there you can see we have a quotient of two functions. G and h is the quotient of the two functions. It says then f prime of x is equal to the following. It's equal to g prime of x, that's the derivative of the top, times h of x, that's the bottom, minus g of x, that's the top, times h prime of x, that's the derivative of the bottom. And that's all divided by the quantity h of x squared. It's the bottom squared. And sometimes that's the way that we read this off in terms of g of x being the top function and h of x being the bottom function. So again, the derivative of a quotient, it's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared is a quick way to read that off. Think of this as kind of being a five-step process, if you will. We talked about chain rule being a three-step process where you have the derivative of the outside function evaluated at the inside times the derivative of the inside, those three steps there. You saw in the last section, actually, product rule is a four-step process, derivative of the first function times the second function plus the first function times the derivative of the second function. Four steps there to go through. Here you actually have five steps. Derivative of the top is the first step times the bottom is the second step minus the top, the third step, times the derivative of the bottom, that's the fourth step, and then all divided by the bottom squared, that's the fifth step. If you think about it in that way, chain rule is three steps, product rule is four steps, and now quotient rule here is five steps. I think that's a nice way to help you remember those properties. Let's take a look at another way that we can write this property down. And we saw this with product rule. We wrote it kind of a little bit faster way to write this, I guess, maybe perhaps even a little bit easier to remember it this way too. Just writing in terms of two functions u and v. If y is equal to u divided by v, then y prime is equal to, it's the same thing of course, just another way to write this. Y prime is equal to u prime times v minus u times v prime all over v squared. But again, that's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Same result there. One thing to note there in that numerator, realize that it's subtraction here. So the order that you do these in does make a difference. If you do the subtraction the other way around, you get the wrong answer. Unlike product rule, since there was addition there, it didn't technically matter whether you found the derivative of the first function times the second and did that first, or found the derivative of the second function and multiplied by the first function. When you added those, of course, you get the same result. Here with quotient rule, with it being subtraction, a different result. You get the opposite answer there if you do it the wrong way around. So it's the derivative of the top times the bottom minus the top times the derivative of the bottom. And in fact, if you look at that numerator, it looks almost like product rule. The only difference is that it's subtraction instead of addition. So if you remembered product rule the way I showed it to you, it's very helpful here in helping you remember the quotient rule. Okay, so that's the quotient rule. We can now find the derivative of a quotient using this property. And just like we did with product rule, the next question is, well, how do we know that that in fact is the case? And so we're going to go through the proof of this. And you can actually use, I guess, either one of these to prove this. I'm just going to use that first form there and think of it as a using function notation. So let's start out with the condition here. It says if h of x or f of x is equal to g of x over h of x. F of x is equal to g of x over h of x. In fact, we'll say let. That's what we usually write down, so I'll put that out front. Let f of x equal that. Okay? And we want to show what the derivative of this function is equal to, and we could go through a similar process like we did with product rule. However, we talked about this earlier, back when we were proving the derivative of cosine, actually. Instead of going through the whole process of using that formal definition of derivative to prove cosine, instead what we did is we had first proven what the derivative of sine was, and then we used that to help us prove the derivative of cosine. It was much faster, much easier way to do it. And actually, we've already proven the derivative of a product in the last section. So we're going to use that to help us here. And I'm going to rewrite this quotient as a product. Let me just get rid of that period that we had there. And let's state that this, of course, is equal to, instead of g of x divided by h of x, I'm going to write it as g of x times the quantity h of x raised to the negative 1. So I rewrite that quotient as a product. I can always do that. You can do this for any quantity there. You can always rewrite from a quotient to a product or vice versa, product to a quotient. But the advantage of writing it this way is, first of all, it's a product of two functions. I know the rule for the derivative of product. If I look at that second function, h of x to the negative 1, that's actually a composite function. H of x is the inside function, negative 1 there as the power is the outside function. I know how to find the derivative of a composite function using chain rules. So I have it in a form that I know all the rules to finding that derivative. So we're going to find the derivative that way. So f prime of x is equal to, follow product rule first because it's a product of g of x times this h of x to the negative 1. So product rule says take the derivative of the first function, g prime of x, times the second function, h of x to the negative 1, oops, and then plus the first function, which is g of x, times the derivative of the second. Now here again, you got to be careful. This is a composite function, so follow chain rule as we do this. Start with the derivative of the outside. This is the first step of chain rule, which says bring the negative 1 out front and subtract 1 from the power. That's the derivative of a power function. Second step of chain rule is you substitute in the inside function. That's h of x. And then finally, we multiply that by the derivative of the inside function. This is the third step of chain rule, which of course would be h prime of x in this case. And there's actually our derivative. We're going to just write this in a slightly different form so I can actually get to can actually show that it's this derivative that I have up above here. Okay, it doesn't quite look the same yet, and we're going to try to get it in that same form here. So let's rewrite this as g prime of x divided by, again, h of x to the negative 1 is the same as 1 over h of x. So I'm going to write it that way. G prime of x over h of x. And then this is actually being subtracted here because of this negative 1 that I'm multiplying by. So I'm going to just make this a minus. I'm going to, again, split this up into the stuff that should be in the numerator, and the other stuff will go in the denominator. So the g of x and the h prime of x go in the numerator, and the h of x to the negative 2, that goes in the denominator. That's h of x squared. Still doesn't quite look like what we started with, but it's getting closer. It just turns out that I just need to get a common denominator between these two in order to add these together, or subtract them really in this case. So if I just multiply this first one by h of x over h of x, I'm going to just kind of squeeze that in here. H of x over h of x is what I want to multiply by. And once I do that, my numerator becomes g prime of h of x times h of x minus g of x times h prime of x. And this is now all divided by my new common denominator of h of x squared. And look at there. There is our quotient rule. Derivative of the top function, g prime, times the bottom function, h of x, minus the top function, g of x, times the derivative of the bottom function, h prime of x, all over the bottom function, h of x squared. So there's our proof of quotient rule. So now let's use that in a couple of examples here. And even though in this proof, by the way, I've used product rule in order to prove it, I want you to use quotient rule to find all these derivatives. So if it starts out as a quotient, use quotient rule. I want you to get used to using quotient rule. So don't try to rewrite that as a product for any of these problems. And that's how I'm going to do these examples here. So take a look at example 1. It says to differentiate, which again, differentiate's just another word that we use to describe finding a derivative. So it's saying find the derivative of this function. F of x is equal to the sine of 5x divided by 8x minus 3. All right, again, the first thing I have to notice is I've got a quotient here of two functions, so my rule that I've got to follow is quotient rule. So let's go through this. Derivative of the top function. Now the top function is a composite function, so follow chain rule as I do this. Derivative of sine of x, my outside function, is cosine of x. Excuse me, it's cosine, I should say, of something. Chain rule says you substitute in the inside function, and again, I like using those parentheses as a placeholder for what would be the x, because they really help me remember there's something else that goes there. It's not going to be just an x. It's the inside function, and then I multiply by the derivative of the inside function, which is 5. And then we multiply that by the bottom function, 8x minus 3, and then subtract the top function, sine of 5x, times the derivative of the bottom function. And the derivative of 8x minus 3 is just 8. All right, again, the derivative of 8x is 8, derivative of the 3 is 0. Again, if you want to write it out that way, you can, but it turns out the derivative is just 8 there. And that's all divided by 8x minus 3 squared, all over the bottom squared. And so just to rewrite this here slightly, let's pull the 5 and the 8x minus 3 out front here. We'll write this as 5 times 8x minus 3. In fact, if you wanted to distribute the 5 through there, you could, times the cosine of 5x. And then we'll put the 8 out front here, so minus 8 times the sine of 5x. And this is all divided by the 8x minus 3. Now sometimes there might be some common factors that you could factor out of the numerator, or even perhaps cancel with what's in the denominator. In this case there's not, so there's nothing more for me to do with this problem. I would leave it just like this. Okay, but if there are other things you could do, the back of the book might do those additional steps to kind of simplify it. But this one is finished. Let's take a look at the next example. Example 2 says, again, differentiates. Another way to say find the derivative of the 5x minus 2. Oops. 5x minus 2 to the 7th. And we're dividing by 4x plus 9 raised to the 3rd power. So again, the first thing you got to recognize is that you've got a quotient of two functions. The numerator is the function 5x minus 2 to the 7th, which happens to be a composite function. The same is true about the denominator. It's a composite function. But the overall, I'm looking at a quotient of those two functions. That's what leads me to use the quotient rule. So follow quotient rule. Derivative of the top function, that's going to be, it's a composite function, so follow chain rule here. So the derivative of the outside, 7 times something to the 6th power. Chain rule says you substitute in the inside function, 5x minus 2, and then we multiply by the derivative of the inside, which is 5. That's the derivative of the top. We then have to multiply that by the bottom, which is 4x plus 9, raised to the 3rd power. And then we subtract the top function, which is the 5x minus 2 to the 7th, times the derivative of the bottom function. Now again, use chain rule here. So chain rule says take the derivative of the outside function, which is going to be 3 times something squared, which then chain rule says you substitute in the inside function, that's 4x plus 9. And finally, we multiply by the derivative of the inside, which is 4. That's the top part. That's all divided by the bottom, which is actually the 4x plus 9 cubed, and we're going to square that whole thing. I guess I'll write it that way first, and then we'll simplify this, but it's all over the bottom squared. All right, so let's just kind of write this a little bit nicer form here, I guess. Let's take the 7 times 5 is 35 times 5x minus 2 to the 6th, 4x plus 9 cubed, minus 3 times 4 there is 12 times 5x minus 2 to the 7th, 4x plus 9 squared, and this is all divided by, I guess we might as well simplify this here. If you take 4x plus 9, cube it, and then square it, we multiply those exponents, remember. So this is actually 4x plus 9 to the 6th power is another way to write that. And you can leave your answer just like that and move on. Okay. However, for a problem like this, I see there's a couple things that I could do. In the numerator, I see that I have some 5x minus 2's here in each one of those terms, so I could combine those two guys, or factor those out, I should say. And secondly, I see that I've got 4x plus 9's in both terms, as well as that's what's in the denominator. So there's definitely some stuff I could factor out and then even cancel out with the denominator. So let's do that in this next step. So the 35 is going to stay in there. There is a common factor of 3, I guess, between the 12 and the or not a count. No, take that back. There's not a common factor between the 12 or the 35, so I have to leave that all in there. But I do have some 5x minus 2's, so I'm going to factor out the 5x minus 2. I have 6 of them in the first term, 7 in the second one, so I can factor out 6 of them. The 4x plus 9's, I've got 3 of them in the first term and only 2 of them in the second, so I can only factor out 2 of those guys. And now what I'm left with, so I've got 35, that constant still there. And the 5x minus 2's, I took all 6 of them out. 4x plus 9's, I had 3 of them. I only took 2 out, so I'm still left with 1 of those, 4x plus 9. 12 still is there. The 5x minus 2's, I factored out 6 of them. I had 7, so there's still 1 of those guys left. And the 4x plus 9's, I factored both of those guys out, so they're both gone. This is all divided by 4x plus 9 to the 6th. So first of all, I see that I can cancel out here. I've now got a common factor in the numerator and denominator of 4x plus 9. I've got 2 of them up here, and I've got 6 of them down here, so that leaves me 4 of them in the denominator. That's the first thing I can do is get rid of those. But then if you look at what I've got in this last factor in the numerator, it's actually just a linear function. 35 times 4x plus 9, that's linear. 12 times 5x minus 2, that's linear. So this is just a linear function. I can even rewrite that just slightly here. So let's do that last step here. So we've got 5x minus 2 to the 6th. I factored, or I canceled out the 4x plus 9's. So I'm just left with this right here. I've got 35 times 4, which is 140 times x. And I'm subtracting 12 times 5x, which is 60x. So we've got 140x minus the 60x. That sounds like we got 80x left over. Or left, I should say, not left over. And then you've got 35 times 9, which is what, 255? No. 270 and 45 is 315, I think. 315. And then you've got a negative 12 times a negative 2. That's actually a positive 24. So that should add up to 315 and 24. It sounds like 339 is what we should end up with. 339. Probably be a good idea to punch that in your calculator and just double check that. In fact, you've got the right calculation there, but that sounds right. And that's still divided by 4x plus 9 to the 4th. So that's the form you might find that answer written in the back of the book. Like I said, you do not need to go to that step for me. You can stop once you get to this point right here. I'd say definitely combine your constants, the 5 and the 7, for example. You get 35. And in the second term, the 3 and the 4, combine those. But otherwise, if you want to check the work that they have done to get their answer in the back of the book, this is the last few steps that you've got to go through to get that. Let's take a look at one last example. And it's derivative of 5 over 7x cubed. Now, if you look at the way they showed you to do it in the book there, they're going to show you to rewrite this one, and probably that makes sense to do that. But again, I want you to have some practice using quotient rule. So I'm going to strongly urge that you use quotient rule even on something like this. Don't try to rewrite it, even though technically it would make the derivative a lot easier to rewrite it. You could rewrite this just as a power function. But I want to show you that you get the same result that you would even with using power rule by using quotient rule here. So let's go through this with quotient rule. Take the derivative of the top. The top function there is just a constant, so its derivative is 0 times the bottom, which is 7x cubed. And then minus the top, which is 5, times the derivative of the bottom, which is a constant times a power function, so it's going to be 7 times 3x squared. And that's all divided by the bottom squared, which is 7x cubed squared. So this turns out to give us, again, the nice thing about that 0 there, this is just gone here. In fact, I might just put the negative out front here, I guess. You've got 5 times 7 times 3, which is, so 5 times 7 is 35 times 3. That'd be 105 x squared. And if I square out the denominator, remember you got to square each term in the denominator. So you've got 49, so it's 7 squared. And you've got, I shouldn't say each term, but each factor of this has to get squared. So the 7 squared is 49, x cubed squared is x to the 6th. And we could simplify that a little bit further with the fact that x squared over x to the 6th, that would simplify to give me just an x to the 4th in the denominator. And in fact, I can factor out a 7 from both the numerator and denominator. If I factor out 7 from the 49, I'll be left with 7. If I factor out 7 from the 105, I'd be left with 15 times 7 gives me 105. So I could rewrite this as a negative 15 over 7 times, I was going to put the x to the 4th in the denominator. So I've got 15 over 7x to the 4th. That's how you could rewrite that. And if you compare that to how we could have rewritten this problem and used power rule to answer this one, let me just show you the result we would have gotten. Let me just show you a second method here. Again, I strongly am going to urge that you use the quotient rule to find the derivative of this, but this is what we would have ended up with. I guess we can write it this way. So the derivative of this is equal to the derivative of this function. I'm going to rewrite this as 5 over 7, 5/7 times, instead of dividing by x cubed, that's the same as x to the negative 3 power. So we've got a constant times a power function here. So the derivative of this is the 5/7 times a negative 3 x to the negative 4. So a negative 3 times 5, that's a negative 15 over 7 x to the negative 4. And of course, I can rewrite that and put the x in the x to the 4th in the denominator and get the same thing that I had up above there. Okay, definitely, like I say, this second method is a lot easier to do, but I want you to get practice using quotient rule. So at least attempt it with that method. You can always go back and double check your work the other way. That is the end of this section for us.